and a warm welcome. It's really nice seeing all of you today. Well, I know I'm not seeing you, but you know what I mean. I thought that before starting with our lecture, it would have been nice introducing myself. So, my name is Mariagrazia. I'm Italian and I come from a very small town in the southern part of Italy. I have moved to the UK about 3 years ago for work reasons, and I'm currently working as a statistical consultant for the Department of Statistics of the University of Oxford. So now let's start with the business at hand. As you can see from this first slide, we're going to talk for about an hour and a half of basic statistics with the hope that by the end of this lecture, you will feel more acquainted with this rather simple but useful concept, which will be helpful for you when you will need to describe your data. So let's see how our lecture is going to be structured. I've thought of dividing it in 4 macro sections. The first section will be about understanding our data. So we're going to describe data types, discuss together about what is that we define as a variable, and describe different kind of data such as grouped and ungrouped data. The second section will be introductory of a concept that you will hear very often when working with data, which is the concept of distribution. In particular, we're going to understand what we intend by a univariate distribution. And in the third and fourth section, we're going to talk about measures that we can use to describe distributions, such as measure of centrality and measure of variability or dispersion. In the fourth section, we're going to talk about and just give some hints of what we intend by bivariate distribution and how we can measure associations between variables using the chi-squared test. Then we're going to wrap nicely what we have learned today and just create some basic visualization with Excel. So, are you ready? Well, I imagine all of you nodding by now, so let's go. Let's start with the first section of our lecture about understanding data. The first question we should ask ourselves is, what do we mean by data? And to answer to this question, I have borrowed this very clear and useful description the United Nations Economic Commission for Europe came with in 2000. So let's read it together. Data is the physical representation of information in a manner suitable for communication, interpretation, or processing by human beings or by automatic means. So from this definition, we can easily understand that data represent the building blocks of any kind of analysis. But let's face it, if we wouldn't have had data, we wouldn't have had anything to analyze. So we couldn't have applied any kind of statistical technique. So data represent the values that we attribute to measurements or observation. Let's think about that with an example. Let's assume we have a GP, a general practitioner who is a doctor in the UK, and they want to measure the blood pressure of one of their patients. So the data for this doctor will be represented by the numbers they can observe in the tool they are using to measuring the blood pressure of the patient. These data are, according to the definition of the UNEC, communicable because the doctor can communicate them to their colleagues, just to update them about the health condition of the patient. They are interpretable because the doctor can understand by using them if the patient, for example, suffers of hypertension, and they can be understood and processed also by automatic means because, for example, the doctor can decide of creating a nice plot which shows the pattern of the blood pressure of the patient throughout a month, for example. So let's consider still within the example of the GP and the blood pressure. Let's assume that one day the GP is in a rush, so they just record the value of the blood pressure very quickly, and they don't realize that they put the decimal point in another place and not where it's supposed to be. So the blood pressure of the patient for that day, instead of being 140.0, will be 1.40. As you can see, this can cause quite a few issues when you go and analyze automatically this data, and it represents another element that we should take into account when considering and talking about data, which is the quality of the data. There is a concept which is generally used in computer science, which says something about rubbish in, rubbish out. And this is very much true in statistics, in my opinion, because if you have very low quality data and you put them in a nicely working model, what you will get out of that will be very low quality estimates. So it's really unlikely you will be able to do anything with them, least replying to your research question. So data quality is really important, and it's also important taking into account the data are measured and classified in different ways, and we need to consider that and be extremely aware that there are different ways of analyzing data which are measured or classified in a certain using a certain criterion. So when I was preparing this slide, I came up with this statement from Donnelly et al. In their publication of 2016, which says, aren't we just talking about numbers here? What could go wrong? Well, plenty can. And in my experience with real-world data, I can say that this is an understatement. So how do we measure data? We have a classification defined by Stevens in 1946, and we have 4 main categories of measurements. So we start with nominal categorical, ordinal, rank level, interval, and ratio. As you can see, they are organized in a sort of ranking as a sort of stair, and this has been done for a reason, because starting from the bottom, so from the nominal and categorical, and going up to the very top, which is represented by ratio, we can say that the information contained in each of these levels of measurement increases while going up to the top. And also the number of mathematical operations which are meaningful and we can actually perform using this data will increase in number when reaching the top of the stair. But now let's go and see in details all of these main categories, starting with the nominal data. So nominal data are represented by numbers which identify mutually exclusive categories, but we cannot do anything, we cannot perform any mathematical operation with these numbers. To understand this better, let's consider an example. For example, here we have the identity card of a person named Martha London, and we have their social security number. Now, let's ask ourselves a couple of questions. Would it be meaningful for us computing the average social security number of all the women in a town? Would it be meaningful for us plotting the social security number over time to see if it has any changes? Well, the answer is no to both questions. So it's a number, but we cannot perform any kind of mathematical information. So we cannot transform the data and put the data together in order to gain more information. Let's now move to the other step of our scale, which is represented by ordinal data. So ordinal data adds an additional information, which, as the name says, it's the order of the different of the points. And we know that points are adjacent, but we don't have information between adjacent points. So let's now consider an example. As you can see, here we have a little sticky man on a podium. And in 2020, following the Tokyo Olympics, the UK had a moment of great excitement because there were 2 Brits who won the diving men's synchronized from the 10 meters platform. So if you're interested, the first place was Thomas Daley and Matty Lee, and then the second place were Chinese divers, and the third one were Russian divers. So we know, like if we look at the podium, we know that the first one will be UK athletes, the second one Chinese athletes, and the third one will be Russian athletes. But we don't have any additional information regarding, for example, the points they scored, which made, for example, the UK athletes being on the upper level of the podium. So, for example, it won't tell us that the UK athletes have scored 20 points more than the Chinese one and 50 points more than the Russian one, for example. So it gives us more information than the nominal data, but still the information is quite limited. Let's move now to the interval data. In this case, they share the characteristics of the ordinal data, but we have an additional information. So we know that the adjacent points are equally distant. And let's think, for example, as to a scale to measure temperature. So we know that 36 Celsius degrees and 37 Celsius degrees are as far apart as 39 Celsius degrees and 40 Celsius degrees. So we know that the difference between these 2 measurements is one Celsius degree. The critical point with interval data is that they don't have an absolute zero. For example, with temperature, which is a very excellent element to think of, if we have zeros in Celsius degrees, this won't mean that we have absence of temperature. This means that we have a very specific temperature at which, in general, it snows. So let's move now to the upper part of our scale, the ratio data. The ratio level of measurement data are the same characteristics of the interval ones, but with the addition of an absolute zero. And in this case, let's consider car speed as an example. So we know that if the speed of a car is 0 miles per hour, we know that the car is actually not moving. It represents the absence of movement. At the same time, we know that if we have two cars, the first car is is moving at 100 miles per hour, and the second car is moving at 50 miles per hour, we can say that the first car is moving twice as fast as the second car. So we have a ratio which is 100 over 50, which is 2. So 2 times quicker than the first car is 2 times quicker than the second one. So now that we have an idea of how data are measured, we can go into the minutiae and try to understand how numerical data can also be expressed. They can be expressed by using integers, so whole numbers, or float. Float numbers are numbers which have a fractional part, so they have a decimal point, and in general they are more precise. They can give you more detail, more granular information about data. This is helpful when we are going to talk about variables. So first of all, let's think about what a variable is. A variable is a measure of a characteristic of interest. It can be, for example, number of children, height, blood pressure, weight, temperature, etc. When the measures are obtained in the context of an experiment, like we talked about in the case of the GP measuring the blood pressure, we would like to be able to understand why the changes we observe actually happen. So we can say that the variables can be classified in 2 categories based on the level of measurements they represent. So we have discrete variables, which are represented by integer numbers. For example, number of children. Now, it's common to hear, especially from official statistics, that they use float number for the number of children, but it's unrealistic thinking that a family can have 1.5 children. It would be rounded up to 2 or down to 1. And, or if we think, for example, of the floors in a building, while continuous variables are measured using floating numbers. In this case, we can add finer and finer information and have more granular information about the variable of interest. For example, height. We can measure it using just meters, or we can add centimeters and millimeters. This will give us an additional and more granular information about the height. Now let's talk about what we mean by grouped and ungrouped data. Ungrouped data are the data that we basically collect when we first perform our experiment. So let's say that our experiment consists in understanding the color composition of a bag of M&Ms. So what we do is, like, we take an M&Ms each time, and then we write down the color that we observe. So we will have a list of colors. If we assume that we have 7 M&Ms in a bag, we will have 7 colors, one next to the other. So brown, yellow, etc. Then when we group this data to be analyzed, what we do is actually creating the distribution of the colors of M&Ms in a bag. So what we are going to do, we are changing the raw data with the count of all the M&Ms of the same color in the bag of M&Ms that we are analyzing. So in this case, we will have that we have 5 brown M&Ms and 2 yellow M&Ms in our bag of 7 M&Ms in total. So now we have, let's kind of gather and sum up what we have learned so far. So we know about data now, we know that they have different level of measurements, and they can be nominal, ordinal, interval, and ratio. We know that nominal data, with nominal data we cannot perform mathematical operation, and they have a very limited amount of information, while with ratio, which is on the other side of the scale, we can perform quite a high number of mathematical operation, have meaningful results. And it contains as a consequent higher quantity of information. We know that numerical variable can be expressed using integer or float numbers, which are more precise. We know about variables that represent the phenomenon of interest that we are analyzing in our experiment, and they can be discrete or continuous. Discrete could be, for example, number of children or number of floors in a building, while continuous can be height, weight, temperature, blood pressure, etc. Then we know that there is a difference between ungrouped and grouped data. Ungrouped data are raw data, so what we collect at first during our experiment, while grouped data are basically what represent the distribution of our data. So now we are ready to move forward. Okay, so now we can move forward to the second part of our lecture and talk more in depth of the concept of data distribution. Then we are going to see some groups of measures which are really helpful when we want to describe our data. First of all, what do we exactly mean when we talk of univariate data distribution? Well, uni comes from one. This means that the distribution is concerning a single variable. A univariate data distribution is helpful to summarize our data and also to represent them graphically. When we have a univariate data distribution, what we can do is answer to questions about the data. Some of these questions could be, what is the most common value in our data? And to do so, we have a very helpful class of measures which are called measure of central tendency or of centrality. Or we can have questions more concerning, let's say, the variability in our data. We want to know how spread our data are. In this case, we are going to use measure of variability or dispersion. Another thing that we can do is plotting our univariate data distribution. In this case, we are going to see, very interested in seeing the shape of our distribution. And this is sort of summarizing in a very nice graphical way what we have investigated more in depth using our measure of central tendency and the measure of dispersion. But let's see an example of data distribution, and let's go back to our M&M's bag. But this time we have got greedier, so we want a bigger bag. We have 51 candies in total, and our idea is to measure, to define the distribution of color in our M&M's bag. So we're going to pick each M&M, and then we're going to record the color. At the end of our experiment, we have found out that 17 M&Ms are brown, 18 red, 7 yellow, other 7 green, and 2 blue, for a total of 51 M&Ms. Another way of representing a data distribution could be grouping the raw data in intervals. The most common example I can think of is the case of age. Let's assume that, for example, you want to you want to define the distribution of age in your classroom at uni. So all your colleagues who are attending, for example, this course of basic stats. So what you're going to do is you want to group your age in classes of 10 years width. So you will have 20 to 30, 30 to 40, 40 to 50, and so on. So you have grouped your raw value of age in a class, in an interval. We're now going to see the first group of measures that we can use to describe our data distribution, the measures of centrality or of central tendency. So what do exactly these measures of central tendency do? They give us an indication of the typical value in our data, which is an effective estimate of the middle point of our distribution. The most well-known measures of central tendency are mean, median, and mode. In a couple of slides, we're going to see how they are kind of working together and in which cases we should prefer one instead of the other. We're going to start the exploration of our measure of central tendency with the most well-known one, which is the mean, and I'm pretty sure you are quite familiar with it. So the mean represents the average score in our distribution. It can be computed on interval and ratio data. And there are different kinds of mean, also if this is maybe not as well known as the concept of mean itself. So we have arithmetic and weighted mean, and then the one that can sound a bit less familiar to you are the geometric mean and the harmonic mean, which we're going to see more in detail in a couple of minutes. First of all, let's focus on the advantages and disadvantages of this measure of central tendency. One of the main advantages is that the mean is computed on the entire sample, so it uses every single value. For this reason, it's a very good representation of it. Moreover, when we are extracting more samples from the same population, the mean tend to be almost the same across all the samples. So we can say that the mean is almost invariant. It resists to fluctuations across the samples extracted from the same population. The disadvantages of the mean are based on the fact that since it uses all the values to be computed, it's really sensitive to extreme values. And another low point of the mean is that it cannot be computed for nominal or ordinal data. So now let's go and see more in detail the different types of mean, starting with the arithmetic mean. If you're not familiar with the mathematical notation, please don't worry about it because we're going to see it together. So this X with the little bar on top represents the mean. N represents the total of observation in our sample. This symbol here means a summation. So we are going to sum all the observations in our sample with I going from 1 to n. Now let's go to see this with an example. So let's assume that we want to compute the mean math score of the students in a class composed of 20 students. So we have all the marks they have obtained in the last math test, and we want to compute the average math score. So we have 20 students. If we go back to our formula, we know that n is 20. And then we are going to sum all the scores from 10 to 6. We sum all the scores and then we divide them by the number of observations. So the average level of math score is 7.35. So if we consider, for example, a range of 0 to 10, we will have that the students of this classroom specifically have, on average, a good knowledge of the subject. Now, let's go and see a concept which is a bit more complicated, which is the weighted mean. As you can see, the formula is basically identical to the one of the arithmetic mean, with the addition of this WI. WI is basically telling us that not all the observations in the sample have the same importance, so they need to be weighted. Let's go and see an example to really clarify this. So now we are going to continue our quest of measuring the math score, the average math score of the district. So in this district, there are 3 different schools. We have school 1 with a mean math score of 8.5 and 100 pupils. We have school 2 with a mean math score of 6 with 200 students. And then we have school 3 with a mean math score of 7.8 and 300 pupils. If we would just sum the mean math score and divide by 3, this would be incorrect because we know that this value has been obtained with a different number of tests. We have different number of students who have taken the test. So first of all, we need to compute the total number of observation, the total number of students in our district, which will be given by N1 plus N2 plus N3. So 100 plus 200 plus 300. Then we are going to compute the weighted values. So we are going to weigh the mean MS score of school 1 per the number of students, 100. And the same we are going to do for school 2, whose weight will be 200, and school 3, in this case, the weight will be 300. So we are going to sum all of this and then divide by the total students, which is 600. And we will have that the mean math score, the average math score of the district, of all the schools in the district, is 7.32. Okay, so now let's go and see more about the geometric mean. The geometric mean is in general used for very specific contexts, such as business or economics. For example, to measure percentage changes over time, ratio, index number, and it can be computed for values which are above than 0. This happens because the geometric mean can be seen as the arithmetic mean of the observations in a sample expressed in a logarithmic scale. So the logarithm is a mathematical function, and as all the mathematical function, it has a sort of realm of existence. And in the case of the logarithm, the realm of existence is composed by all the positive numbers. So the logarithm doesn't exist in 0 or for value less than 0, so negative. And since it doesn't exist, we cannot compute it. So basically, in the formula of the geometric mean, we have a new symbol that we hadn't seen in the arithmetic or weighted mean. This symbol is basically identical to the summation, but instead of summing the value, is multiplying them from 1 to n. And in this case, we are elevating all the multiplication of all the scores in our sample to the power of 1 over n. The power of 1 over n can be written as the nth root of the product of all the observations in our sample. So now we are going to see this applied to the example of the math score, but this wouldn't be the most appropriate mean to use in that case, because we know it would be better using the arithmetic mean or the weighted mean. So we want to compute the geometric mean in this case. 20 will become our root, and then we are going to multiply all the scores from 10 to 6. In this case, our geometric mean will be 7.10. Now, let's go and see the harmonic mean. The harmonic mean is the arithmetic mean of the reciprocal of each of the n scores in the sample. So basically, as you can see, here we don't have xi, we have 1 over xi. This is the inverse, the reciprocal of the observation xi. And we will have n at the numerator instead of being at the denominator in this case. In general, harmonic means are used in situations in which the scores are represented inversely. So for example, time rates, prices, etc. Let's go and apply this to our usual example of the math scores, even though also in this case, it wouldn't be the most appropriate mean to apply. So we are going to put 20, which is our total number of observations at the numerator, and then we are going to see, to put the inverse of the marks at the denominator and summing them. So we will see that our harmonic mean is 6.79. Now, you may have noticed something, but let's sum up with this slide. So if we would have a distribution in which, or a sample in which all our data would be identical, so without variability, in our example of the marks, all the students have the same mark, we will have the arithmetic mean, geometric mean, and harmonic mean will be identical. The same, of course, will be worth for the weighted mean. In this case, in our case specifically, we don't have all the students with the same mark. We have different marks, so we have a higher variability. So in this case, you can see that the arithmetic mean is greater than geometric mean, which is greater than the harmonic mean. The more the variability increases, the more the difference between the different kind of means increases. Say that about the mean, we can move to another measure of central tendency, the median. The median is literally defined as the value that divides into the distribution. So it has the same number of values above and below it. When we compute the median manually, we need first to arrange the value in ascending order. Then we need to assign a position or rank on each of the values. And also when we compute the median, we need to take into account the number of observations, if they are odd or even, because there is a different formula. Let's go and apply what we have just said about the median to our example of the math score. We have 20 students, so our sample is even in this case. What we're going to do is reordering all the marks. So we will have 3, which is the lowest one, up to 10, which is the highest one. And we're going to assign a position to each of them. So 3 will be in position 1, 5 will be in position 2, and this last 10 would be in position 20. Then we compute x as n over 2, which is 20 over 2, 10. And we're going to consider the position 10 and the position 10 plus 1, 11. Then we are going to divide them by 2. This value will represent the value of the median. So we are going to take the value in position 10, 8, the value in position 11, 8. We are going to sum them and divide by 2. So we obtain that the median of this sample is 8. Let's consider a class with an additional student, so it's 21 students. We reorder again in ascending order our marks. 3 is position 1, 10 is position 21. We are going to compute x as n over 2, which will be 10.5. Then we are going to add 0.5 to the x we have computed, and we will obtain the position of the median. So 10.5 plus 0.5 is 11. The value in position 11 is 8. The median math score is 8. Then we close with the last measure of central tendency that we are going to talk about in this lecture, which is the mode. The mode is the most frequently occurring score in the distribution in the sample. When we have a unimodal distribution, this means that we have just one most occurring value, but they can be more than one, and in this case we talk of multimodal distribution. The mode is literally the only central tendency measure that can be computed for nominal or ordinal values. Let's go to our example of the marks. We can build the distribution. We have all the marks here, and then we have the frequency. So how many times they occur in the sample? We have that the mark 8 will represent our mode because we have that 6 students over 20 have a mark of 8. So 8 is the most occurring value in our distribution. So let's do a recap of our measure of central tendency. When we choose between the different measures of central tendency, we need to make sure that the value that we get from them will be the best representation of the most typical value of our distribution. The mean is the only measure of central tendency which is computed on the values, but because of that, it can be really sensitive to extreme values, and we're going to see this very quickly with a small example. So when we have extreme values, choosing the mean may not be the right choice. So in this case, we could use the median. The median is less affected by them because it's computed on the ranks, not on the values. But as the mean can be computed only on numerical values. In the case we have nominal or ordinal level data, in that case, the only measure of central tendency we can actually use is the mode. Let's see an example about the sensitivity. Let's see now a short example about the sensitivity of the mean to extreme values. So let's assume that the professor marking the math exams makes an error. Instead of writing 10, they write 20. So in this case, if we go and compute the arithmetic mean, we will have that the average math score of the class will be 7.85, when originally with the correct value of the mark was 7.35. So the typo has increased the value of our mean of 0.5 points. While if we compute the median, we will have that the median value will still be given by the average of the values in position 10 and position 11. So it will still be 8. So now we have concluded with this second chunk of our lecture, and we can sort of sum up the main highlights of this section. We have learned about data distribution. We know that it's a very useful concept to summarize data and even represent them graphically. We know that there are different kinds of measures which help us to describe a distribution. Among those, the measure of central tendency are really helpful. The most common known measure of central tendency are mean, median, and mode. The mean, as is computed in general for numerical values, has some advantages and disadvantages. Among the advantages is that we can use all the values of the sample to compute the mean, so it's really representative of the sample at hand. But the reverse coin of this advantage is that it's really sensitive to extreme values. So if we have a sample which has a lot of extreme values, we may need to go for a different measure of centrality, which is, for example, the median, which being computed on the ranks is less sensitive to extreme values. The mean is the value which divides into the distribution. So we have the same number of values above and the same number of values below it. When we have categorical or ordinal, nominal or ordinal ranked data, the only measure of central tendency we can actually use is the mode. So the main takeaway is that we need to choose the measure of central tendency which gives us the best representation of the typical value of our sample. Now we can go and see the measure of dispersion or variability. So now let's see another set of measures we can use to describe our data distribution, the measure of variability or dispersion. The measures of variability are summary statistics which give us an indication of the amount of dispersion present in our data. While the measure of central tendency were giving us an idea about the typical or most common score in our distribution, the measures of dispersion are basically telling us how far from the center the data points tend to fall. If we have a look at the figure here on the right side of the screen and we focus first on the left side curve, we will see that since the mean is represented by the center of our distribution, the data points are pretty clustered, pretty close to the mean. So this means that the data distribution of which this curve is a representation is characterized by low variability. While if we have a look at the curve on the right, we will see that the data are quite spread out with respect to the center. So the data distribution here is characterized by high variability. So why is it so important for us knowing about the variability present in our data? Well, if we have low variability, we have a sort of consistency in our data, while if we have high variability, we may expect to incur in more extreme values. So basically, knowing about the variability will tell us how likely will be that an unusual event may happen. So for example, let's apply the concept of variability to a real life case. I commute to the office using by bus. I know that the bus will show up at the same time every day following its timetable. I know that it may be 2 minutes early or 2 minutes late, but it will definitely show up around that time, and this will make me on time for work. What would happen if the bus would appear at a different time every day without any way for me to actually knowing when the bus is showing up? This would mean that I may arrive very late at work. So knowing about the variability of my bus timetable, I could decide that instead of going by bus, I could go by car and be on time, for example, for the first meeting of the day. So there are different measures that we can use actually to measure dispersion in our data. The most common ones are range, interquartile range, variance, and standard deviation, which we're going to see more in detail in the following slide. So let's start with the range, which is the most straightforward measure of variability to compute. It is computed as the difference between the highest value of the distribution and the lowest value of the distribution. Now, you may guess that this can come with some issues because, first of all, we are just focusing on the extreme of the distribution and we are not paying much attention on what is happening in the middle. Then, if there are extreme values, we will have that the range will be highly influenced by them, even though if they are atypical or, for example, they are typos. Moreover, the range is really influenced by the sample size. When the sample size increases, the range increases as well. So if we want to compute, for example, the variability of two groups using the range to compare them, we need to make sure that they have almost an equal sample size. So let's see an example. We have two groups of students, of 20 students each, and we want to compute the range of the marks they've obtained in math. So what we are going to do in class 1, we are going to subtract from the highest mark, which is 10, the lowest one, which is 3. So our range will be 7, while in the second class, the highest mark is 8 and the lowest is 5. So the range will be 3. We can say that in class 1, the math scores are more spread out than in class 2, because we know that there is a difference of 7 points between the best performing student and the worst performing one. A very good way to deal with extreme values when computing variability is using as a measure of dispersion the interquartile range. The interquartile range is basically the range in the middle 50% of our distribution. It is computed as the 75th percentile minus the 25th percentile. So basically, if we look at the figure here, what we do is like we trim out the 25% on each side of the distribution, and we take just the 50% in the middle. So the interquartile range will be represented by this area here. Before we start talking more in depth of the interquartile range, I feel that we need to introduce two important concepts, the concept of percentile and the concept of quartile. So what do we mean with percentile? A percentile is each of the 100 equal-sized groups into which a population can be divided, and a percentile represents a sort of threshold below a certain percentage of values fall. So let's go back to our group of students. In this case, we are interested in their height. We know that one of our students is 1.85 meters tall. So it will be the fourth tallest in a group of 20 people. This means that 80% of the students in the group will be less taller than them. So 1.85 will represent the 80th percentile. So what are the quartiles? Quartiles are specific percentiles. We have the first quartile, which is the 25th percentile, and below the first quartile, there is the quarter of the distribution with the lowest value. Then we have the second quartile, which is the 50th percentile, which basically divides the distribution in two. It has the same number of values above and the same number of values below. Now, does this ring a bell? Well, it is the median. It is exactly the median. Then we have the third quartile, which is 75th percentile. Above the third quartile, we have the quarter of our distribution with the highest values. So the interquartile range is computed as the third quartile minus the first quartile. Now let's see an example. The interquartile range is very much computed as the median, so we need to reorder the marks. Then we build our frequency distribution. We have the absolute frequency, which will give us an indication of how many times a certain mark is present in our group of students. So we have that the mark 3 is present once, the mark 8 is present 6 times, etc. The total is the total number of students, 20. Then we compute the relative frequencies. To compute the relative frequency, we need to divide the absolute frequency by the total of observation. So we will have that for mark 3, the relative frequency will be 1 over 20, 0.05. And we compute in the same way all the other frequencies. The sum of the relative frequencies is always 1. Then we are going to compute the cumulative frequency. The cumulative frequency gives us an indication of the values which are above or below a certain threshold. So you can see that are really helpful for us because we want to compute the quartiles. So how do we compute it? We start with the first relative frequency, 0.05, and we sum it to the second one, 0.15. Then we sum it to the third one, 0.15, which will be 0.30. So we will have that 0.30 will be our first quartile. So this means that below 0.30, we have the quarter of the distribution containing the lowest values. Then we go ahead and we compute the third quartile. This means that the quarter of the distribution above the third quartile will be the one with the highest values. So what do? We take the value corresponding to the third quartile, which is 8, and we subtract from 8 the value of the first quartile, which is 6. So we have that our interquartile range is 2. So this means that basically in the 50% middle of the distribution, the students may have a difference up to 2 points in each mark. Now let's see another measure of variability, which is, I think, more well known than the others, and as the mean is computed on all the values of the sample. We're talking about the variance. As you can see, the variance can be computed as the difference of each observation in the sample from the mean squared and divided by the number of observations. The difficulty with the variance is that as much as we know that when the variance is higher, the variability is higher, it's really difficult to interpret because it will be expressed in squared unit measure of the variable for which we were computing the variance. So if the variable was, for example, seconds, we will have the variance expressed in seconds squared. So it will be quite difficult actually interpreting the single value. For this reason, we use the standard deviation. The standard deviation is basically the most typical deviation of the data points from the mean, and is computed as the square root of the variance. So as you can imagine, it will be on the natural unit of measure of the variable that we are considering. Here I've added a note. The value of sigma, which is our standard deviation, and sigma square, which is our variance, cannot be negative. This happens for a mathematical reason, because as we can see here, we have a squared term. We know that a square of a negative number is a positive number, and the square of a positive number is again a positive number. So the value of sigma and sigma square cannot be negative. Let's see an example. We want to compute the variance of the math scores in our 20 students group. So we subtract from each of the score the value of the mean, we square it, we sum, and we divide by the number of observation. We have that the variance is 3.03 points square. Very difficult to interpret. So we compute the square root, the standard deviation, which is 1.74. What does it mean? It means that each mark can differ between minus 1.74 and plus 1.74 from the mean. This is actually giving us a very good information, which is that the scores in the sample are not too far from the mean, are not too spread. So the variability of the sample is not too high. So how can we choose the measure of variability which is more appropriate for our data? Well, what we need to bear in mind is that we need to have an idea of how far the data points in our distribution fall. So for example, if we have a very small sample size, or if we are comparing sample of a very similar size, then in that case we can compute the range. But bearing in mind, if that we have extreme values, the value of the range will be biased. So if we have extreme values or extremely skewed distribution, so distribution which have very heavy, very chubby tails, then it would be more appropriate for us applying the interquartile range or any other percentile-based rank. For example, if we are interested in more than the 50% middle of our distribution, we can compute also the difference between the 97.5 percentile and the 2.5th percentile, which will include 95% of our data. Of course, the bigger the range, the bigger maybe the variability falling in that group of data. While when we have like a pretty symmetric, so not too skewed the distribution, we can compute the standard deviation, which is also pretty straightforward to interpret. And we prefer the standard deviation to the variance because the variance is expressed in squared unit of measure, which make the concept more difficult to actually understand and deliver and interpret. So now we know everything about univariate distribution and how to describe them by using measure of centrality or measure of variability. And we can do our upgrade to bivariate distribution and to how to understand the association between two variables by using the chi-square test. So a bivariate distribution is a distribution which involves two variables. And the easiest way to describe a bivariate distribution is by means of a bivariate table or contingency table. So here, for example, we have a fictitious data set of 356 observations, 356 people that have been polled about their smoking habits and socioeconomic status. So we have that on the rows, we have the smoking habits, so current, former, and never. And on the column, we have the socioeconomic status, so low, mid, and high. We have that the intersection of each row and each column represent the number of people, for example, in this case, who are current smoker and have low socioeconomic status. The sum of the row will represent the marginal distribution of smoking habit. It will tell us across all the socioeconomic status the number of current smokers, former smoker, and never smoker, while the sum of the column will give us the marginal distribution of the socioeconomic status, because it will tell us across all the type of smoker habits, how many people are in low socioeconomic status, how many people are in the middle, how many people are high. The sum of the total of the row and the total of the column gives the total of observation. So, what is the chi-square test and why do we use it? The chi-square test for association of the independence of two variables is used to determine if there is any association between two categorical variables. It is based on a contingency table as the one we have seen in the previous example. And in order to compute the chi-square test, it's necessary that the categorical variable have at least two categories. And we have seen that in our previous example, we had smoking habits and socioeconomic status, each with three categories. As all the statistical tests, the chi-square test has some assumptions. The first assumption is the independence of observation. So the categorical variables are not paired. This means that, for example, we are not measuring the association between the socioeconomic status of a group of people before they won the lottery and after they won the lottery. So we assume that the group of the categorical variables are independent. And the sample size, because we need to have enough in each cell in order to perform a chi-square test and have reliable, so robust results. So at least in the intersection of the majority of cells, so we say 80% of our contingency table, we need to have at least 5 observations. So how is the chi-square statistic computed? The chi-square is computed as the difference between the observed counts, which is given by the value in the intersection between the ith X variable and J X variable, and the expected count, which is given basically by the total of the observation. So the chi-square is actually telling us, is a number which tells us how much difference exists between the observed counts and the expected counts if there will be no difference between the two populations. Then, as in every statistical test, we compute the degree of freedom. The degree of freedom are basically the number of parameters which are sort of free to vary, but we're going to see a description later on in this presentation. And the degrees of freedom in this case are computed as number of rows minus 1 per number of columns minus 1. So let's see an example. We want to investigate if there is any relationship between the level of education and the gender in a specific community of people. So the level of education will be high school dropout, high school graduate, some college, bachelor's degree, and graduate degree. As we can see, we have 5 categories, so we have at least 2 categories. And then we have gender, female and male. And in this case, we have 2 categories. So we can tick something in our checklist if we can apply a chi-square test. The other thing we need to observe is if we have a big enough sample size. As we can see, in all the intersection, we have more than 5 observations. So we can go ahead with the chi-squared, assuming also that the level of education and the gender are independent. So what do we need to do is compute the expected counts, because the observed counts, we have them, for example, for high school dropout and female is 486. For computing the expected count, we take the total of the rows, so the marginal distribution of high school dropout, and we multiply it by the marginal distribution of female, like the total of the marginal distribution of female, and we're going to divide them by the total of observation, which is 3,800. This will give the value of the expected count. We do the same for all the level of education and for male. So we then compute the chi-square statistic, observed minus expected square divided expected, and we obtain 35.57. We then compute the degrees of freedom, which are given by number of rows minus 1 per number of columns minus 1, which is 4. We have the level of significance, which is 0.05, which is it's a common concept in statistics, which I'm sure you are going to see more in depth in inferential statistics, but it's basically the probability of rejecting the null hypothesis when it's true. 0.05 is a sort of trade-off between 2 types of error that you are going to see more in detail in the inferential statistics class. So this is the level of significance. And then we have the chi-square values, which is 35.57. In order to understand if this value is higher or lower than a certain other value, we need to use something which is called a table of chi-square. The table of chi-square gives us a value of a critical value given based on the level of significance, the degrees of freedom, and the sample that we have available. So in this case, we have that the critical threshold is 9.49, and we have that our chi-square statistic is higher than this critical value. So being the chi-square statistic higher than the critical value, we can reject the null hypothesis. The null hypothesis is that there is no association between level of education and gender. So we can state that actually there is an association between level of education and gender. Now, we mentioned degrees of freedom. Let's see an example. We are hosting a dinner and we need to seat 10 people. We know that knowing where the first 9 guests are sitting, we can determine where the 10th is going to sit. So basically, we can choose freely where the first 9 are sitting, and then the 10th will come as a consequence based on where the first 9 guests have been sitting. So our degrees of freedom will be given by 10 seat minus 1, which is the blocked one, the one that will depend from the previous one. So basically, the degrees of freedom give us an idea of the amount of independent piece of information which went off in calculating the statistic. The degrees of freedom typically equal the dimension, the size of our sample, minus the number of parameters we need to calculate during the analysis. And usually it's a whole positive number. So earlier we have seen some introductory concepts about bivariate distributions, and we have learned how to measure associations between 2 categorical variables using the chi-squared test. So now we should know all about how to represent using summary statistics some aspects of our data distribution, such as, for example, the measure of centrality, the measure of variability. So we have an idea of the most difficult score, we have an idea of the dispersion, but what we haven't seen so far is how to have a look at the shape of our distribution, so how we can represent graphically our data. Okay, so now we are in Excel, and you may recognize this dataset because it's the one we have been using for measuring the association between level of education and gender in the chi-squared test example. So we know that we have like all the level of education, we have gender, and the number in the intersection between, for example, high school dropout and female indicates the number of female subjects who have dropped out of high school. Now I highlight all my data. Then I click on insert, and Excel has a very helpful command, which is recommended charts. So I click on that. And then I want to represent my data using an horizontal bar chart, which is the first suggestion. I make it bigger so we can see it better. Then I can change the chart title. And as you can see here, we have some buttons which we can use. For example, I click on this one, and there are a lot of elements we can be adding to our plot. For example, I think that I think would be useful would be including axis titles. So we know what we have on the x-axis, which in this case is the number of subjects. And on the y-axis, we will have the level of education. Oh, sorry, some spelling mistake. Education. Yeah, perfect. Then clicking again here, we can, for example, add the data label. So we know exactly how many subjects we have between, for example, male and female who are in the graduate degree level of education. Then if we click here, we can change the style of our plot. So for example, if we like something else, like maybe with white labels or something like that, but I will stick with the one suggested by Excel. And then we can change the palette of colors. So I will go with this one, and in this case, yellow will be male and orange will be female. In this case, this filtering value, this filtering button will let us choose how many, like which are the values that we want to display. For example, if we want to just focus on high school graduate, if we want just to see the female of our sample, we can then work on that. Now, let's say that we have changed our mind about the plot. So we want to modify it. Let's go on design. We can click on change chart type, and then we can go and choose another type of graph, for example, column. So we want a vertical bar chart. In this case, the number of subjects will be on the y-axis, while the level of education will be on the x-axis. Female and male will be always the coloring of each of the categories. Let's say we want to change it once more, and we want to completely change the representation. So in this case, we will have what is called grouped bar chart, and we will have female and male on the x-axis. So we need to change level of education with gender. And we have the number of subjects on the y-axis. And in this case, each of the column will represent a level of education. So there are several different types of plots that we can use, and we are going to see them now back into the presentation using a different data set. Just to have a quick recap of what we have seen on Excel, we can highlight our data set, create our plot by clicking on suggested plots, and then we have these buttons over here which are really helpful. The plus button, it's helpful to add labels, title of the plot if it's not available, labels of the axis, data label to know more about, for example, more precisely about, for example, how many male there are in the graduate degree. Then this other button is helpful to change the style of the plot or the color, while this button here is really helpful to filter out the information that we have available and we want to display in our plot. This is another way of representing the same information. While this one is an horizontal bar chart, this one is a vertical bar chart. So as you can see, we have not changed much the information. We have decided, for example, to switch the colors. So the orange one will be female in this case, while the blue one will be male. We can represent the same information using this grouped bar chart. So we have female and male on the x-axis, and in this case, the different bars will be represented by the level of education. So the legend is going to tell us, for example, the blue is high school dropout, while the gray is some college, etc. Now let's go and see another example. We have the marks that the students of a class grouped in female and male, have obtained on a number of essays. So we want to see the distribution of the marks these students have obtained. To do so, the best plot is called box plot. And let's see the components of this plot, which is really informative. So we have this X here symbol, which represents the mean value, while this bar over here represents the median value. Then we have that the top of the box is represented by the third quartile, while the bottom of the box is represented by the first quartile. So it gives us an indication of the variability that we have in our data. We can see that in female, the variability is higher than in male. Then we have these lines over here, which are called whiskers. And in particular, this line here is represents the third quartile plus 1.5 per interquartile range. We know that the interquartile range is given by Q3 minus Q1, while this line over here represents Q1 minus 1.5 per interquartile range. These lines here are called whiskers, as I said, and they are very helpful to understand which are the boundaries within which we consider a value not an outlier. So if we have something which is greater than this value or smaller than this value, then it probably will be highlighted as an extreme value. Also, we can see that here the mean is quite close to the median, so we don't expect the presence of too much extreme values, which may skew somehow our distribution. Let's go and see another example. Here we have the distribution of BMI per gender. So we have female, male. For some classes of BMI, we don't have value for male. And we're going to see, we're going to plot it using this valuable kind of plot called histogram. This gives us an indication of the shape of the distribution. For example, we know that for male, it's quite bell-shaped. So we expect it to be quite symmetrical. While for female, we have like the tail looks to be a bit heavier than with respect to male, but it still looks quite symmetrical. So it's another way to have a look to our data. You can absolutely play with Excel and just, trying to figure out which is the best plot that is of interest for you. So now we are going to have like some references here if you want to go back and just read more about what we have learned in our lecture. Just to do a quick recap of the main takeaways. So we know now about different kind of level of measurements for our data that we know we need to really pay attention to. So we know that we can have, for example, nominal or ordinal data, or we can have interval and ratio data. Depending on the level of measurement of this data, we can apply a different number of mathematical techniques. Then we know that we can have distributions, so we can group our raw data in order to understand, for example, how many times a certain value is present in our sample. We know that when we have a unique variable, we talk about univariate distribution, while when we have two variables, we talk about bivariate distribution. We know that there are some measures like summary statistics that we can use to describe our data distribution. We have measures of centrality, and in particular, we've been seeing the mean, the median, and the mode. We know that when we choose the measure of centrality, we need to really take into account which is the best one to represent our data. We know that mean is computed on the entire sample, so it's a very good representation, but at the same time is sensitive to outliers. So extreme values which can be potentially considered outliers. And when, in these cases, when we have a lot of extreme values, it would be better using the median because it's more stable since it's not computed on the values, but on the ranks associated to the values. Then we have the mode, which is the only measure of centrality we can actually use when we are working with categorical or like nominal or ordinal data. Then we've seen the measure of dispersion or variability, and in particular, we have had a look to the range, the interquartile range, the variance, and the standard deviation. We know that the range is pretty straightforward, but it has some flaws. It depends, it varies with the sample size, and also taking into account just the extreme of our distribution. It's very sensitive to extreme values, so it may not be a good representation of our sample if we have extreme values. In this case, it's better going for the interquartile range, which is given by the third quartile minus the first quartile, or any kind of percentile-based rank. For example, since the interquartile range is the 50% middle of our distribution, we may be interested in having a bigger portion of the distribution in our interquartile range, so we can, in our interpercentile range, so we can do a difference, for example, between the 97.5 percentile minus the 2.5 percentile. And in this case, we will have 95% of the distribution. Then we've seen the concept of variance and standard deviation, which tell us the typical deviation of each of the observations from the mean. We prefer the standard deviation to the variance because the variance is expressed in unit squares. So in the unit square of our the variable that we are measuring. So if we are measuring, for example, time in seconds, it will be in seconds squared. So it will be more difficult to interpret, while the standard deviation, being the square root of the variance, will make the interpretation easier. Then we have seen a few graphics that we can use to represent our data with Excel. I hope that you have enjoyed this lecture, and I wish you good luck for the rest of your curriculum of studies.